So I'm going to talk a bit about some parameterization results in valued fields and some Pila-Wilkie type results. And this is joint work with Raf Cluckers and Halupczok, who are both here. Where is he? Okay. Let's see. Okay. But the plan for the talk is to first talk about parameterizations in R and the usual Pila-Wilkie theorem, just to give you some kind of background for this. And then afterwards, I'll talk a bit about valued fields and how to approach this problem there. So let's see. Okay. Okay, so the definition of parameterization is fairly simple. So I'm just going to give it immediately. So if X is a subset of 0, 1 to the n, then a parameterization of X it's just a finite set of maps, say from open interval 0, 1 to the m to x, such that the images of the phi i's together cover all of x. So at this point, there's absolutely no, there's nothing interesting going on. There's no conditions at all. So if R is a natural number, then we call it an R parameterization if each of these maps is CR, and we want something slightly more, we want some good bound on the CR norm of this phi I. So, and moreover, if you take the CR norm, so that's just the largest size of some derivative of these phi i's, where now j is at most R and x runs over the domain. Well, I guess here probably you should put some open subset of this thing. And this should be at most 1. Okay, so one way to think about this parameterization is that there are some kind of charts for x in some way. So let me make a drawing of what I mean. Okay, maybe x is something like this. So you want to find some parameterization for this strange set x. Or maybe this entire business is the image of one of these maps, phi I. Another one is this single point. That's totally fine. It's allowed. Then there's this sort of squiggly line. And it might be too squiggly so that you cannot cover it with just one of these maps phi I because of this derivative condition. So what you can do maybe is cut up this part into finitely many pieces. And on each piece, find one of these maps phi I with this good derivative property. And then there's this final part where there's some kind of bad singularity maybe. So maybe we put the singularity as a constant map on one of these, and then for the other, we take these two branches to sort of avoid this singular behavior. Okay, there's one more thing I have to say. This integer m here, it should be equal to the dimension of x. But in this definition, of course, the dimension x doesn't make sense since it's just some arbitrary subset. But in a minute, we'll work in, I don't know, some Tame setting where every set has actually a dimension. And then we really require this condition. Okay. Okay, so let me talk a bit about some existence results for these parametrizations. So the first results are due to Guillaume and Guillaume. We show that every semi-algebraic subset of 0, 1 to the n has a semi-algebraic R parametrization. For every integer R, there exists such a thing. And here, what do I mean by a semi-algebraic parametrization? It just means that all of the maps phi I themselves are semi-algebraic. So you sort of stay within the same setting of definable sets. And so here we have a notion of dimension, of course, so this integer m should be the dimension. Okay, so their motivation, okay, so maybe a few more things. So Guillaume originally proved this slightly weaker version where you're allowed to avoid a small subset of X, some kind of subset of volume at most epsilon. And this makes it easier because then you can avoid sort of neighborhoods of really singular points and things like that. And then Gromov showed that actually you can cover the entire set with these parametrizations. And so their motivation came originally from entropy and topology, but nowadays these parametrization results are used a lot in counting. And so, for example, Pila generalized this to parametrizing subanalytic surfaces, but probably the most well-known parametrization results is due to Pila and Wilkie, who show that if X is definable in a no-minimal structure, then X has a definable R parametrization for every integer R. And here definable means that you stay within the same no-minimal structure. Okay. Now there's another theorem with the name Pila-Wilkie, the counting theorem, and this is actually the main ingredient in proving this kind of result. So let me explain this counting thing, where we will count rational points on transcendental sets and show that these do not have so many rational points. Okay. Any questions so far? Okay, so we will be counting rational points on sets. So let me first, well, you have to put in some restriction on the rational points because in general, even transcendental sets could contain infinitely many rational points. So we need this notion of height. If I take some rational number A over B, then we can assume that they're co-prime. And the height of this rational number is then defined just to be the maximum of the absolute values of the coordinates. And this just sort of measures how complicated this rational numbers. And if I have a tuple of rational numbers, then the height is just the maximum of the height of the coordinates. Okay, now if I have a subset X of R to the n and some integer B, we can define the counting function which is just going to count the number of rational points on X of height at most B. So it's going to be nxb, which is the number of points on X, which are rational, and their height is at most B. And we want to study the behavior of this function as B increases. Okay, and what are the sets we will be counting on? They will be transcendental parts of definable sets. So let me explain what this means. So if you have some x definable in a no-minimal structure, then it can, of course, have lots of rational points. But the idea is that if you throw out, so if you, for example, have a semi-algebraic set, then it can contain many rational points. But the idea is if you throw out all of these semi-algebraic sets, then you're left with something without many rational points. So x-alg is the algebraic part of X. This is the union of all positive dimensional connected semi-algebraic sets contained in X. So this is called the algebraic part of X. And then there's the complement, which is called the transcendental part. Transcendental part of X. Okay, so this is sort of a strange object. Let me give you some examples. For example, if you take X to be the graph of the exponential, well, as you would expect, this contains no semi-algebraic curves or anything. So the transcendental part of X in this case is just X itself, as you would expect. But here's another set. Let's look at all X and Y, for which, let's see, maybe Y strictly less than X plus X. So this one also sort of looks transcendental, maybe. But actually, this set is open. So whatever point I take, I can find some small semi-algebraic curve through it. So in this case, the transcendental part is actually empty. So even though it might look a bit transcendental, transcendental part could be empty. And third, if you start with some definable object, then in general this transcendental set, the transcendental part will not be definable anymore. So the classical example, something like this. You take all x, y, z, such that x to the y is equal to z. So what's the algebraic part here? This is going to consist of all of the elements in here for which y is rational. So in particular, this is sort of like infinitely many curves inside of this X. So this algebraic part has infinitely many connected components, and also the transcendental part will also have infinitely many connected components. So this is very much not definable in any O-minimal structure anymore. Okay, nevertheless, you can try to count rational points on this transcendental part of X, which is exactly what Pila-Wilkie theorems is about. So it says the following: let X be definable in an O-minimal structure. Then for every epsilon, there exists some constant C, which can depend both on X and on epsilon, such that if I count the number of rational points on transcendental part of X of height at most b, this is bounded by C times b to the epsilon. So it's some subpolynomial growth of the rational points for every epsilon. Okay. And as you're probably aware, there's some really nice number theoretic applications nowadays. Okay. So how is this linked with these parametrizations? It might look a bit surprising. Here you're somehow counting rational points. Here you're creating charts somehow for this set X. So how could you ever go from these parametrizations to this kind of counting result? So the idea is that if you have some parametrization like this, then there's a way to catch all the rational points on X itself in some small number of algebraic hypersurfaces. And you can imagine that these algebraic hypersurfaces, they will sort of be contained or contribute mostly to this algebraic part of X. So in this transcendental part, you have thrown it out, and you shouldn't actually be counting the rational points from there. Okay. Is it visible now? Okay, any questions about that part? No, okay. Okay, so let me now get to valued fields. Where I want to begin with a similar Pila-Wilkie type result in QP, p-adic numbers. And we'll be working in this structure called QP-an, which is just QP with the valued field structure, together with symbols for convergent power series. So we're going to add symbols F for all convergent power series on ZP. And so this structure was first studied by the Neff and Van den Dries, and they proved some kind of quantifier elimination result, which in particular shows that this structure enjoys many Tame geometrical properties. So in the words of something from earlier this week, this structure is what's called 1H minimal. This was explained by Sylvain. So you have, like, definable functions will be differentiable. You have dimension theory, cell decomposition, all of these nice results. And there's a Pila-Wilkie theorem in this structure, which I want to explain. So again, we're going to count rational points on transcendental parts of definable sets. So we have to define this counting function and this algebraic part, or the transcendental part of X. So the counting function is just completely identical. The rational points are contained in QP, so there's no issue there. But for this algebraic part, you have to be a bit more careful, because in the definition it says you remove all connected semi-algebraic sets, but connected doesn't make sense in QP. So you have to be a bit more careful there. So first, let's define what dimension is here. So if I have some definable set, X in QP, then we say that dimension of X is D. Okay, nice. Okay. Sorry. The dimension of X should be the largest integer D, such that there exists a coordinate projection from QP to the N to QP to the D, such that pi of X has interior, or has non-empty interior. And then we say that a set X is of pure dimension D if locally around every point of X it has dimension D. So if for all x in X, and for every open ball, or open or closed ball around X, the dimension of X intersect with B is equal to D. So this just sort of says that locally around every point you look like something D-dimensional, and this should be the analog of connected, sort of. Okay, so then what should the algebraic part be? This should be the union of all, what did you say there? So, all pure dimensional semi-algebraic subsets of X. Let's see, and semi-algebraic, what does it mean? It means definable just in the language of rings or valued fields. That's the same. So without these power series. And again, the transcendental part is the complement of this algebraic part. Okay, so with all of these definitions set up, we can write down the Pila-Wilkie theorem, which is due to Cluckers-Comte-Loeser. So let X in QP to the n be definable in this analytic language, so in QPN. Then for every epsilon, there exists some constant depending on X and on epsilon, such that if you count rational points of height at most b on this transcendental part, you get the usual, or the expected thing, namely b to the epsilon. So it's again a subpolynomial. Okay, and there's some extensions of this. So there's work of Cluckers-Forey-Loeser, who prove some kind of uniform in P version. So where now X is maybe defined in some language where you also have convergent power series, but maybe only with coefficients from Z, so that it makes sense in every QP. And then this would say that for P large enough, this constant here is not dependent on P. Or I guess for every P, then it will not be dependent on P. And this also gives you these kind of results in positive characteristic local fields then. Okay, so what do we do? So this is in some kind of specific setting, namely you're working with these subanalytic sets. So what we do is we generalize it to the full H minimal setting. So let X now in QP to the n be definable in a 1H minimal structure. Then you have the same kind of bound. So for every epsilon, there exists a C. Such that this counting function is bounded by C times b to the epsilon. Yes?
Should the structure expand QP, or is it just a 1H?
Yeah, so this automatically extends the field language. Or is that the...
Is it for QP or for any 1H value space?
Well, X is in QP to the n.
Okay,
Yeah, but actually that's a good question. So we prove it more generally in any valued field. So you could put any k here, or actually it's here. So this works in any mixed characteristic 1H minimal field. So for example, something that's new is maybe you look at CP with some analytic functions, and then you still get this kind of bound. Another question? Or?
How does this make sense? I mean, the rational numbers will still be in the prime field.
In here? Yes, but the set itself might be definable with way more stuff. Yeah. Yeah, so in some sense, indeed, the rational points, well, they're still sort of contained in a smaller subset. Yeah. Okay, but that's not, I mean, here you cannot put CP. I mean, so we show that you can put CP, but I mean, in this result, you cannot, their methods do not work for CP, is what I meant to say. So what's sort of going on is that this constant C, here it depends on the size of the residue field, sort of. But for us, it depends on the characteristic of the residue field. Okay, so how do you prove these kind of results in valued fields? So the approach is the same, sort of. So the idea is to start again with these parametrizations, because once you have these parametrizations, I told you can try to catch these rational points in algebraic sets using what's called the determinant method. And this works really well, except what you really need as input for this determinant method is that these maps from the parametrization, these phi i's, that they are well approximated by their Taylor polynomials. And so if you look at the definition here, so in the real context, this follows from this condition on the CR norm. Maybe if you're working on a connected domain and your function is CR and with some good bounds, then automatically, because of Taylor's theorem, the function is approximated by its Taylor polynomial and the error term is given by the next derivative. But this is completely false in the valued field setting because the spaces are totally disconnected. And what's written here is really a local condition. So it's only saying something at a point. So if you want some kind of Taylor approximation, you need it globally, then there's no way to go from this kind of condition to some global approximation of a function by its Taylor polynomial. So sort of this definition of parameterization is not correct in the valued field setting. And the solution is to work with the notion of parameterization where it's this entire thing plus these phi i's are approximated by their Taylor polynomial. And then the issue is, of course, to show that these exist in general. Okay. So let me talk a bit about this. So parameterizations. So we'll define them, what they should be in valued fields. Yeah. Okay, so maybe some notation. Since this stuff makes sense, well, also now this Pila-Wilkie theorem makes sense in any valued field. K will just be any valued field. OK will be the evaluation ring. Mk is the maximal ideal. The valuation, let's say, little k is the residue field. And I denote valuation multiplicatively. So from k to gamma k with a norm symbol, just because it's closer to the intuition from the real numbers. What else? So we will work in some language L, expanding the language of valued fields. So it could be maybe this analytic language over here. And the assumption is that k is 1H minimal in this language L. Okay, so let me just give you some examples of 1H minimal structures you can keep in mind. So for example, yeah? Oh yeah, it contains, for sure, yeah. It could just be QP itself, or you could add these analytic structure. This is a good example of a 1H minimal structure. Or if you want something with residue characteristic 0, you can maybe take C double brackets T, or add some p-adically convergent power series and things like that. Okay, and so this 1H minimal thing, it's very useful because it's some Tame geometric framework, so it automatically implies that definable functions will be differentiable away from some finite set. You will have cell decomposition, and so also dimension theory, and we use that kind of thing all the time. Okay, so now let's try to define the correct notion of parametrization in the valued field setting. So first, some more notation about Taylor polynomials. So let's see if x is some function from some open subset of k to the n. And let's say it's CR on the neighborhood of some point y. And I take some integer r. And then we define the Taylor polynomial just in the usual way. Of order less than r, of f at y, to be this, well, just the usual Taylor expansion. And there's some notational tricks hidden here in this I, so it's some multi-index. And the I factorial is like the product of the factorials, and here it's also, okay. You get the ID. There. Okay. So let's define one more thing. Okay, so let's now define what the maps phi I should satisfy. So we want the same condition as here, and also this good approximation by its Taylor polynomial. So let's say we have some integers r and n. Okay. And we have some function f on some open subset of the valuation ring. And we say that it is tr. If f is CR on X, this, well, the same thing, this CR norm, we'll use the same notation. Is at most 1. And for x and y in X, we want that f of x is close to this order r Taylor polynomial of f at y, which I mean that it's at most x minus y to the power r. Okay, maybe we call f tr, but this time the tr is at the top. We need some kind of recursive definition, so we also want the derivatives of f itself to be like tr minus 1 and tr minus 2, and so on. So if f is tr minus I for I at most r. Okay, and so usually you would put here maybe the norm of the art derivative or something, but this is bounded by 1 already, so we just put 1 here. makes it a bit easier. And these TR maps, they will replace these phi i's in the definition of a parameterization. So, okay, maybe very quickly, what does T0 mean? There's no Taylor condition in that case, and it just says C0, so this is the same as continuous. What is T1? This just means that f is C1, and the Taylor condition in that case says that f is 1 Lipschitz. So C1 is like a local condition, and Lipschitz is a global condition since it has to hold on the entire domain. Okay, so now we can define what the parametrization is. Let's say that x in OK to the n is a definable set of dimension n. Then a TR parametrization of x is a finite collection of TR maps from, let's say, phi I in OK on some open subset of OK to the m to x. So this is in OK to the n, such that x is the union of the images. Okay, and so as I told you, this sort of TR notion is better behaved in valued fields because of the total disconnectedness. Okay, any questions? Put this one up. Okay, so what do we really prove, or what's the main ingredient for this counting theorem? It's some parametrization result, showing that sets can be parametrized. Okay, so K, as before, is a 1H minimal field, but we need two more assumptions. I will discuss them after I write down the statement. So first, assume that K has algebraic Skolem functions. And two, there exists some integer b, at least 2, such that the beat powers in K have finite index. In K, then every definable set in OK to the n has a definable TR parametrization. Okay, so what are these two assumptions? So one, this is some weak version of definable choice. So this means that every finite to one definable map, let's say from X to Y, between any two definable sets should have a definable section. Has a definable section. So definable choice would tell you that just every definable map has a definable section. So this is some weak version of this. And now it might seem, so many fields don't have this condition. So for example, or maybe here you could also put CP on. I mean, CP does not have these algebraic Skolem functions because there's, for example, no way to pick a root of a polynomial. So even if X and Y are finite sets, then this might fail. However, what you can always do in H-minimal structures is sort of expand the language without destroying H-minimality until you obtain this property that you do have algebraic Skolem functions. So what you can often do is go to some kind of larger language, then you have these parametrizations maybe, then you use them for whatever you want, and then maybe you go back to the original language if you want it. But for example, for this counting, the conclusion says nothing about any definable set or something, so we may as well assume that we have these algebraic Skolem functions at our disposal all the time. Okay, and yeah, and then condition 2 is just some condition on the field itself. But I should also say that in this counting result, you see, I mentioned this works in any mixed characteristic H-minimal field, so also fields where this is not true. And so what we actually do for this kind of result is, instead of trying to parameterize the entire set, which is certainly sufficient for counting, we actually sort of leave out a small part, or maybe we only parameterize some set which contains certainly the rational points. And for this, you do not need this second condition. So this is in some sense closer to Yomdin's original result, where you parameterize not the entire set, but you leave out some small epsilon neighborhood of something. Okay. So what's some kind of crucial tool to obtain these parametrizations? It's that functions, definable functions, can be well approximated by their Taylor series or Taylor polynomials. I mean, it's clear that you will need it because it's in the definition of these TR maps that you need the functions to be well approximated. So something we also prove is that this is indeed true, that definable functions are well approximated by their Taylor polynomial. So that f from k to the n to k be definable. Let's say we have some integer r. Then there exists a definable map. Let's call it chi from k to the n to rv to the n. So let me recall what this means. This is k modulo this 1 plus maximal ideal, such that for every open fiber, f of chi, and all elements x and y in this open fiber. First of all, f is CR on all of f. and on all of f, maybe we shouldn't call it f, let's call it b. On all of b, f is approximated by its Taylor polynomial. So f of x minus the Taylor polynomial of f at y of order strictly less than r. This is bounded by, okay, we have the notation, this CR norm of f times x minus y to the power r. Okay, maybe what is up with this chi map? So you should think of this chi as a cell decomposition. And this is just saying that on the open cells of the cell decomposition, you have Taylor approximation. That's exactly what this is saying. So for n is 1, this was already known. So this appears in the first paper on H-minimality. So we extend it to higher dimensions. Okay, let's see the time. Yeah, I think I will stop there. Thank you.
My question is just the chi map has finite range, right? Or
No.
okay.
It's yeah, cell decompositions are just a bit different in the H-minimal setting. It could be the RV map itself, for instance. So yeah, in O-minimality you always have finitely many cells to do it, but here you will need infinitely many things in general. Yeah. So if it's the RV map itself, then like every fiber will be some small open wall, and you have Taylor approximation on this small open wall.
Okay, thanks.
When you need to increase the language in order to get your scaling functions, do you know more or less what is it that you're adding? Is it too insane to describe?
Well, you can. It's not too well. What you can do is just add literally everything on RV. Like every subset is definable on RV itself.
Uh-huh.
And yeah, that's way too much. Okay, so. Yeah, exactly. Yeah. So you only need these algebraic scaling functions on RV. So if you can do it in whatever way you like on RV, and then you get it in the valued field.